Hello learners, and welcome to our KMO1 KTO4 session on problem-solving principles and techniques. Today we are going to go deep into how we, as production supervisors, identify problems, understand them properly, find their real root causes, and then implement corrective and preventive actions that actually work. By the end of this session, you should not only know what tools like PDCA, DMAIC, the 5 whys, cause and effect fishbone diagrams, troubleshooting, corrective action, and preventive action are. You should feel confident to use them in real production situations. I want you to think of a time on the shop floor when the same problem kept coming back. Maybe a machine that keeps stopping, a defect that keeps appearing, a quality complaint that keeps repeating, or a team conflict that never really goes away. Often, that happens because we fix the symptom and not the root cause. Today's session is about moving away from quick fixes and moving towards structured, professional problem solving. Let's start by looking at the overall idea of problem-solving models. Then we will break them into specific tools. In production supervision, we don't just randomly solve problems. We follow structured models. The main models we'll focus on are 1. PDCA, plan, do, check, act 2. DMAIC, define, measure, analyze, improve, control. 3. A general root cause analysis RCA mindset. I want to walk you through each one slowly and connect them to your daily supervisory role. PDCA is a continuous improvement cycle. It is a simple loop that we repeat over and over as we improve processes. 1. Plan. In the plan phase, we clearly define the problem or improvement opportunity, set goals, and decide what changes we want to test. We collect data, study the current situation, and identify possible causes. As a supervisor, this might involve meeting with your team, reviewing quality reports, and identifying where performance is not meeting targets. 2. In the do phase, we implement the change or solution on a small scale. We test the idea, not roll it out everywhere immediately. For example, if we think a new inspection step will reduce defects, we try it for one shift, one line, or one product first. 3. Check. In the check phase, we compare the results of our test to our expectations. Did defects reduce? Did downtime reduce? Did cycle time improve? We look at the data and feedback from operators to decide whether the change worked or not. 4. Act. Finally, in the act phase, if the change was successful, we standardize it and roll it out more broadly. We update work instructions, train operators, and build it into normal procedures. If the change didn't work, we learn from it and adjust our plan. The cycle then starts again. PDCA is powerful because it encourages us to test changes, learn from evidence, and keep improving instead of assuming that one idea is perfect the first time. Fits perfectly into a supervisor's daily routine of small, continuous improvements. PDCA is one continuous improvement model. Another powerful, more data-heavy model is DMAIC. DMAIC is often used in Six Sigma and structured improvement projects. It is very useful when we have recurring problems that impact quality, cost, or delivery. 1. Define. We start by clearly defining the problem. What is happening? How big is the impact? Who is affected? For example, our defect rate on line 2 has increased from 1% to 4% over the last month. In this step, we describe the gap between current performance and expected performance. 2. Measure. Next, we collect data. We measure current performance accurately. Defect counts, types of defects, where they occur, when they occur, and under which conditions. As a supervisor, you may pull reports from quality systems, tally sheets, or check sheets filled in by operators. Analyze. In the analyze phase, we look at the data to identify patterns and possible causes. We may use tools like Pareto charts, trend graphs, 5 whys, and fishbone diagrams to drill deeper into what might be contributing to the problem. We separate opinions from facts. We ask, what is the data telling us? 3. Improve. Once we have a good idea of the root causes, we design and test solutions. This could mean changing a method, adjusting a machine setting, improving training, changing material specifications, or clarifying an instruction. We pilot the improvements, just like in PDCA's do and check phases 4. Control. Finally, we put controls in place to maintain the improvement. This may involve updated SOPs, revised inspection steps, new checklists, training refreshers, or control charts to monitor future performance. The goal is to prevent the problem from returning. DMIEC is particularly powerful for bigger, more complex problems where a quick fix is not enough. As a production supervisor, you may not run full Six Sigma projects, but you can still use the logic. Define clearly, measure accurately, analyze deeply, improve thoughtfully, and control consistently. Both PDCA and DMIEC support one critical mindset, focusing on the root cause, not just the symptoms. Root cause analysis, RCA, is not one specific tool. It is a way of thinking. It means we are not satisfied with surface-level explanations like operator error or machine failure. Instead, we ask, what exactly caused this? What in our system allowed it to happen? Key ideas in a root cause. Focus. 1. We use facts and data, not just opinions and blame. 2. We accept that usually more than one cause contributes to a problem. 3. We look at systems, processes, methods, training, maintenance, and management, not just people. 4. We apply structured tools like 5 whys and fishbone diagrams to explore deeper causes. As a supervisor, having a root cause mindset means you stop asking, who did this? And start asking, what in the process allowed this to happen? The 5 whys is a simple but powerful technique where we ask why multiple times, usually between 3 and 5 times, to dig below the surface of a problem. 1. Purpose of the 5 whys. The purpose of the 5 whys is to move from symptom to root cause. Instead of stopping at the first answer, we keep going deeper. This prevents us from wasting time fixing symptoms while the real cause remains untouched. For example, if a machine stops, the first why might reveal that a fuse blew. But if we stop there, we will simply replace the fuse. By continuing to ask why, we might discover poor maintenance, overloading, or incorrect installation is the real issue. 2. How the 5 whys works, step by step. Step 1. Clearly state the problem. For example, the machine stopped during the afternoon shift. The problem statement must be specific, observable, and factual. Step 2. Ask, why did this happen? And record the answer. For example, because the motor overheated. Step 3. Take that answer and ask, why did that happen? Why did the motor overheat? Because the cooling fan was not working. Step 4. Continue to ask why until you get to a root cause that you can act on. You might end up at, because there was no preventive maintenance schedule for cleaning the cooling system. We usually reach a root cause between the 3rd and 5th. Why? If we stop too early, we may only fix a symptom. If we blame a person because the operator didn't check, we must ask one more why. Why was the operator not trained or supported to check? The 5 whys is most effective when used with the people who are closest to the work: operators, technicians, and team leaders. As a supervisor, you can facilitate a short 5 whys discussion during a shift meeting. 1. Present the problem clearly. 2. Write each why and answer on a board or flip chart. 3. Involve different team members and encourage honest input. 4. Check that the final cause is something you can act on, like a process weakness, training gap, or missing control. Example walkthrough problem. There is a high number of rejections for missing components on the final assembly line. Why? 1. Because operators sometimes forget to fit the component. Why? 2. Why do operators forget? Because the work instructions are confusing and the step is not highlighted. Why? 3. Why are the work instructions confusing? Because they were never updated when the assembly procedure changed. Why? 4. Why were they not updated? Because there is no formal process to review and update instructions when changes are introduced. Now we have moved from blaming operators to identifying a system gap. No formal change management for work instructions. Correcting that will have a lasting impact. A cause and effect diagram, also known as a fishbone or Ishikawa diagram, is a visual method of organizing possible causes of a problem under key categories. 1. Purpose of the fishbone diagram. The fishbone diagram helps teams to A. Brainstorm all possible causes of a problem. B. Group causes into logical categories. C. See the big picture of what might be contributing to the issue. D. Identify the most likely causes for deeper investigation. It is especially useful in manufacturing environments where many factors, machines, people, materials, methods, environment, and measurement can influence quality. Structure of the fishbone. The diagram looks like the skeleton of a fish. 1. The head of the fish is the problem or effect we are trying to understand. 2. The main bones represent major cause categories. A common set of categories is the sex, man, people, machine, method, material, measurement, mother nature, environment. 3. Smaller bones branch off each main category and list specific possible causes. Step 1. Clearly define the problem and write it at the head of the fish. Example: increased defect rate in product XYZ. Step 2. Draw the main backbone and the major cause branches, for example, people, process, equipment, materials, environment, management, or the 6 Ms. Step 3. Brainstorm possible causes with your team and place each cause under the correct category. For example, under people, we might list new staff not fully trained. Under machine, we might list worn tooling or inconsistent pressure settings. Step 4. Once the fishbone is filled, review all the causes and highlight the most likely or highest risk ones. These become the focus of deeper analysis or trials. Example of a fishbone in production. Imagine we have a problem. Decreased product quality on line 3 on a fishbone. People, insufficient training, lack of supervision, fatigue on night shift. Methods, unclear work instructions, complex changeovers, inconsistent inspection methods. Machines, uncalibrated equipment, worn seals, lack of preventive maintenance. Materials, variable supplier quality, incorrect material handling, contamination. Measurement, inaccurate gauges, infrequent checks, poor data recording. environment, poor lighting, excessive noise, cluttered workspace. As a supervisor, you would use this diagram to guide your next steps. Which areas need data, trials, or corrective action? Often, we use a fishbone first to identify possible causes. Then we apply the 5 whys to the most likely causes to dig even deeper. Together, they provide a strong structure for root cause analysis. So far, we've looked at tools that help us understand causes. Next, we'll move into troubleshooting, the hands-on process of diagnosing and fixing issues. Troubleshooting is the practical side of problem solving. It is the process of diagnosing problems in a system and then taking steps to restore normal operation. 1. Purpose of troubleshooting analysis. The main purpose of troubleshooting analysis is to 1. Identify and address issues that hinder optimal performance. 2. Reduce downtime and scrap. 3. Restore equipment and processes to stable operation. 4. Prevent recurrence through learning and improvement. Troubleshooting is not just try something and hope it works. It is a systematic, step-by-step approach, problem identification. First, we must define clearly what is wrong. This might mean listening to operator reports, observing the process, checking performance metrics, or inspecting a defective product. Vague statements like, "it doesn't work," must be converted to specifics like, "the machine stops after 3 cycles," or "the product leaks at the seam." A. Data collection. We collect relevant information, error codes, times, conditions, which shifts are affected, how often it happens, and what changed. Recently, new material, new settings, new staff. Both quantitative data numbers, times, counts, and qualitative data, observations, comments, matter. B. Root cause analysis. We use tools like 5 whys, fishbones, and is-not analysis to identify the most probable causes. We ask, what changed, what is different between when the process works and when it fails? C. Solution development and implementation. Once we have a working hypothesis about the root cause, we design solutions. This might involve adjusting parameters, replacing parts, revising a method, adding a check, or improving training. We implement changes in a controlled way. D. Monitoring and feedback. After the fix, we watch the process closely. Has the problem disappeared? Has a new problem appeared? We gather feedback from operators and check data to confirm whether the solution is effective. Troubleshooting techniques. Is-not analysis. We clarify what is affected and what is not. Which machines, which shifts, which products, which customers. This helps narrow down possible causes. Step-by-step testing. We change one thing at a time and observe the effect. If we change too many factors at once, we cannot tell which change made the difference. Cross-functional teams. We involve maintenance, quality, engineering, and operators to get a complete picture. As a supervisor, your role is to coordinate troubleshooting efforts, keep communication clear, ensure safety during tests and adjustments, record actions taken, and ensure that learning is captured and shared. You don't have to personally repair every machine, but you must lead and oversee the entire troubleshooting process. Once we identify and fix the problem, we must formalize corrective action and then go one step further to preventive action. Corrective action is the structured response we put in place after identifying a root cause. It is not just fixing it once. It is changing the system to prevent recurrence of the same non-conformance. Purpose of corrective action. The aim of corrective action is to 1. eliminate the root cause of a problem. 2. Ensure the problem does not come back. 3. Demonstrate control to customers, auditors, and management. A good corrective action process includes 1. Clear description of the problem and its impact. 2. Evidence of root cause analysis, for example, 5 whys, fishbone. 3. Detailed corrective steps. What exactly will change in the process, training, material, or equipment? 4. Responsibilities. Who will do what and by when? 5. Verification. How we will check whether the corrective action is effective data, audits, observation. Preventive action is proactive. Instead of waiting for problems to occur, we identify risks and implement measures that stop issues before they arise. 1. Purpose of preventive action. The goal of preventive action is to reduce risk before failure occurs, strengthen systems and processes, protect customers, equipment and staff, support continuous improvement and long-term reliability. 2. Identifying risks. We can identify risks based on trends in data, small increases in defects or downtime. Near misses. Events that almost caused harm or failure. Audit findings. Weaknesses in compliance or controls. FMEA results. Failure modes with high risk ratings. Operator feedback. Concerns and suggestions from people doing the work daily. Examples of preventive actions are 1. Introducing a preventive maintenance schedule based on machine history and manufacturer recommendations. 2. Improving training and onboarding to prevent errors caused by inexperience. 3. Simplifying a process to reduce the chance of human error. 4. Improving storage and labeling of materials to prevent mix-ups. 5. Strengthening quality checks at earlier stages of the process to catch issues before final production. Preventive action links strongly to continuous improvement and planning. It is a sign of a mature operation when the team does not wait for failures but constantly scans for what could go wrong and addresses it early. In KTO4, we explored problem solving as a complete system. We looked at structured models like PDCA and DMake. We focused on root cause thinking. We practiced tools such as the 5 whys and fishbone diagrams, and we linked these to troubleshooting, corrective action, and preventive action. As a production supervisor, your effectiveness is not only measured by how you react to problems, but by how you think about them, analyze them, and prevent them. These tools will help you prepare for your assessments in EISA, but more importantly, they will help you lead your team through real operational challenges on the shop floor. I want you to leave this session asking yourself, when the next problem occurs, will I just fix the symptom, or will I apply these problem-solving principles and techniques to build a better, stronger system? That mindset is what separates a reactive supervisor from a strategic production leader. Thank you for your participation and attention today. Goodbye.